Hi guys, welcome to your first set of notes in Algebra 1B. Today we will be starting Unit 1 with Lesson 1 on the real numbers. Today's unit, or rather this whole unit, is all about radical expressions. Cool. We'll start out today by talking about real numbers, and then tomorrow will be the distance formula. Then we'll simplify radical expressions. After we simplify them, we'll add and subtract with them. And then finally, we'll solve equations. Okay, cool. All right. By the end of the day, our goal, our objective here, is that you will be able to describe the relationships among sets of numbers, among types of numbers. So if at any time you need more time to think about this video, go ahead and hit pause or rewind in case you need to see something again. Okay, so we're going to look at different sets of numbers. So you have this space in your notes. Go ahead and split them in half. Split this space in half with a line like this. I'd leave a little bit of space at the top for our title. Split it in half, and then in one of the halves, you're going to want to draw 3 circles. We're going to split this part into 4 different sets. So you'll have the whole space counts as 1 space. Oh my goodness. This counts as 1 space, and then within that you'll have 3 smaller circles. In our smallest circle, we are going to write so we're going to look at all the different kinds of numbers, the different sets of numbers. When you look at a set, don't think of like a volleyball move or like a movie prop, whatever. A set is like it's an arrangement of numbers. It's a grouping of numbers. It's like a collection of things that you can put in a basket. I like to think of sets as a basket because you put things inside of it. You'll also notice that if you have a basket, if you have a set, you can put that within a bigger set too. So you can have sets in sets in sets. For example, if we start with our smallest set right here, when you think of numbers, even if I ask my niece, who's 4 years old, about numbers, she'll think of the most basic numbers like 1, 2, 3, 4, etc. We'll include 8 because that's my favorite, blah, 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 and you just keep going. So natural numbers include numbers like 40 and 31 and 157, just normal numbers, that kind of thing. We call these the natural numbers. I can make that even bigger. Natural numbers. Okay, there you go. So natural numbers, we can abbreviate this group, this set, with N. We say N represents the natural numbers. These are the counting numbers, numbers that, a preschooler would use to count. So then after preschool, you graduate, you go to kindergarten, and you learn of a new number. This number is 0. And you're a little confused because you're like, how can you have 0 things? You just don't have things. But you learn to use 0 in a placeholder in numbers like 40 and 10 and whatever. So 0 is a number. So once you include 0 with your natural numbers, we're going to call these guys whole numbers. When you think of a whole number, you can include 0, 1, 2, 3, 4, and keep going from up there. So our next set that we'll abbreviate W is called the whole numbers. Whole numbers are our counting numbers, our natural numbers, and 0. Moving on out, once you leave kindergarten, you go on to first grade, and you start subtracting. You start going backwards on your number line, and you realize that in addition to 4, 3, 2, 1, 0, you can keep going, and you get numbers like -1 and -2, -3, etc. You have, -8 and -40 and -239. Okay, we call these guys integers. So an integer is, yes, any negative number, 0, or any whole number. So we say 40 is an integer because it's inside the integer circle. and 2 is an integer because it's inside the integer circle. -3 is an integer. That's great. 3 is an integer, but -3 is not a natural number because it's not within this circle. Does that make sense? And then we have one bigger set of numbers that we like right now. And these are numbers like 1/2 or 0.33333, continuing, or 4/50, or -3/5, things like that, right? These numbers we call rational numbers. We call them rational because they can be written as a ratio. For example, if we have 1 pizza for every 2 people, everyone gets a half of a pizza. Or if there were 5 problems on your homework and you completed 3 of them, you get 3/5 of the credit. Or whatever, right? This is a ratio. And rational numbers include any decimal that ends. So we could do like -0.41. Sweet. We call that a terminating decimal. Or any decimal that repeats, like 0.3333, which is, fun fact, equal to 1/3. Because these are all able to be written as fractions. This is the same thing as -41/100. They can be written as a fraction. They can be written as a ratio. So our last set on this half of our numbers, we say Q. Oh, I missed the integers in our little explanation. Okay, Q represents the rational numbers. We'll go back and fill in that blank. Q represents the rational numbers. They can be written in the form of A/B. They can be written as fractions, or they have decimals that repeat, like 0.6666 or 0.250000. We say that, this guy right here is a repeating decimal because it's the same thing as 41000, and that 0 is the thing that repeats over and over and over again. Here the 3 repeats over and over and over again, which means it can be written as a fraction. Yay, fractions! Fractions, we love them. Ratio means it can be written as a fraction. That's the important part. And to get all our blanks in, we forgot to fill in the integers. Integers are the natural numbers and their negatives, basically. So you have your counting numbers, 1, 2, 3, 4, 5, 0, so 0, 1, 2, 3, 4, 5, and their negatives. So you have 0, plus or minus 1, plus or minus 2, plus or minus 3, that kind of thing. Now this is great. It's a great way to sort numbers, to classify them, say what kind of number you have. And we like these kinds of numbers. If you guys are in art class, I used colors for a reason. These are all cool colors according to your color theory because they help us keep our cool. These numbers are cool numbers. We like them. We know they're not too stressful. They're not too weird. We've got fractions, we've got decimals that end or repeat, we've got normal numbers. That's cool. But what we don't like, what's weird to think about, is not the rational numbers, but rather the irrational numbers. We're going to put that on the other half, and we're going to spell it correctly. Irrational. Put that on the other half of your chart. The irrational numbers are numbers that are, wait for it, not rational, which means they can't be written as a fraction. These are weird numbers. These are numbers like the square root of 5, which is like 2 point something weird, right? Or negative square root of 2. It's like negative 0.14 or negative 0.41 something gross, ew, right? There are numbers like pi, which you might have seen before, which is about 3.141592653, but it just keeps going and it doesn't repeat. There are other numbers, like you can make one up, like 1 0 1 0 0 1 2 3 1 1 2 3 4 1 1 2 3 4 5. Right, okay, like you can see the pattern that I'm doing, but it doesn't have a repeating block, right? You've got 1 0 and then 2 zeros and then 3 zeros and then 4 zeros. That's a pattern, but it doesn't repeat. What would repeat would be something like 0.1 0 1 0 1 0 1 0, etc. Because you can take this 1 0 and that keeps repeating over and over again. So if you had a number like this, because that's a decimal that repeats, that's actually a rational number. Boop. So that goes on that side. We could write that as a fraction by saying that is the same thing as 10/99ths. So there you go. So irrational means, irrational. To be irrational means it cannot be written as a fraction. It's not a fraction. It's not repeating. It is irrational. So this is a nice summary. If you like words, you can keep this part. If you like pictures, like I do, you can use this part. I recommend you have them both and color code them for your notes. Now, some of you have already noticed a pattern. You say, oh yes, I see the abbreviation. We have N for natural. We have W for whole. This is totally making sense. I love math. I love when math makes sense. And then you get here and you're like, wait, hold up. Z for integers? I see no Z here. Well, there's a Z in 0, but that's not helpful. Where does this come from? And here is a fun, free fact for you. It actually comes from German. You have ganze Zahlen, which is German for whole number. And that's why we use Z. So that's a fun fact. You don't have to know that. Also, you get here and you're like, wait, R should be rational. Why do we use Q? That's because if you look at this guy right here, that's a fraction. And Q stands for quotient. Quotient means divide. It's like the answer to a dividing problem. Oh, and hey, look, you've got a division symbol. It literally looks like a fraction, so it represents all the rational numbers. Ha ha ha. That's what it's for. And then P, irrational, we can't use I because I stands for imaginary. We'll talk that in a little bit. We just kind of use P. I don't really know why. If you want to look it up for extra credit and report back, you let me know, and I would love to know. So these are a whole bunch of different types of numbers. When we look at all the numbers together, a way to categorize all the numbers, we call them all the real numbers. Oh, hey, look. That's the title of our lesson. Ha ha ha. Cool. Okay. The real numbers. These are numbers that are real, that exist in our world. Real is as opposed to imaginary. We will not be using that in our class. We will not talk about imaginary numbers, so don't worry about that. So there you go. Those are all the different types of real numbers. Now for our lesson today, we are going to do two things. One, we're going to say where a number belongs. I'll give you a number and you tell me, oh, it's natural. Oh, it's an integer. Oh, it's irrational. So you'll classify a number and then you'll estimate a number too. So let's start it out. Let's start with number 3. Were I to look at my chart, I would see that the number 3 belongs to the natural numbers. Because here it is. Ready? It's right here. It's natural. But it's also, in addition to being in the natural circle, it's also a whole number because it's in the whole circle. It's also an integer because it's still within there. And 3 is a rational number. So we can check almost all those boxes. 3 is whole, 3 is an integer, 3 is rational. Now it's not irrational because you can't be both rational and irrational at the same time. So it's not that. We're going to leave that blank. Let's look at 5/20ths. 5/20ths is a fraction, and that should be cueing you into, no pun intended, cueing you into Oh, I guess the word is clue, isn't it? Ha ha ha. Okay, well, there should be cluing you into the fact that it belongs to Q, because it's a quotient. It's the same thing as 1/4, which is a rational number. It can be written as a fraction. Now, it's not an integer, because it's not like what we consider a whole number, positive or negative. It's not a whole number, it's not a natural number, it's just rational. Now let's look at the square root of 24. The square root of 24 is not a nice rational number, because in order to be a nice rational number, to take a square root, you need to have a square root of a perfect square. And I've included the first 7 perfect squares right here for your convenience. 24 is not on this list. 25 is, and it's close, but close doesn't count. So it's not going to be rational. It is going to be straight up irrational. Cool. And finally, number 4. Oh, how convenient was that? We still have our perfect squares on our list. So the square root of 16, if we go down into our list here, we'll find the square root of 16 is 4. So that means this is negative 4. If we were to go back to our chart, we would see that negative 4 is not a natural number, it's not a whole number, but it belongs into the integer circle, belongs right here in the integer circle. And all integers are in our rational numbers too. So that means that that exercise 4, which is negative 4, is a rational number, because it can be written as a fraction. Say, Ms. Van Dyke, this doesn't look like a fraction to me. Well, I'm about to show you something super mathematically fun. Ready? Negative 4 is the same thing as negative 4 over 1. Boom, fraction. Ha! There you go. All right. Now we have 2 more activities. Our second activity, I guess, is we're going to use a number line to visualize our square roots. So here, earlier, we had the square root of 24. Let's put that on our number line. So there are 2 ways to find approximation. One, you can plug it in your calculator and be like, oh, haha, yeah, it's approximately 4.89. Oh, but I said tenths, so it's approximately 4.9. There you go. Or you can look at it on a number line by looking at this. Well, 4 is the square root of 16. We saw this up here. And 5 is the square root of 25. So here we have 2 numbers on our number line, 4 and 5. And if we were to put the square roots between here, well, that's the square root of 16, square root of 17, square root of 18, square root of 19, 20, 21, 22, 23, 24, square root of 25 is 5. So that's a nice convenient way to put square roots on a number line. And then you can say, oh, well, the square root of 24, that's right here. And as you can tell, it's much closer to 5 than it is to 4. So that's a nice way to visualize where the square root of 24 lies on our number line. Visualize where it lies. Haha. Now let's go to the other side and use a negative number. Now we had to be a little bit careful here, because negative means we count backwards. So if we had, a normal number line, remember that it would look like if you had, 1, 0, -1, -2, -3, -4. We're going to take this portion right here. We're going to zoom in on it, because -3 is the square root of, or is the negative square root of 9, and -4 is the negative square root of 16, because 3 times 3 is 9, and 4 times 4 is 16. So I guess I should have used yellow for that, huh? Oh wait, watch this. Take my scissors, highlight these guys, make them all yellow. There you go. All right? Now, if I want to estimate the square root of -11, I can add those to my number line. So that was the square root of 9, square root of 10, 11. Of course, this is all negative, so we're counting backwards. 13, 14, and 15. So if we wanted to find the square root of 11, I used blue. So it's right here. The square root of, or the negative square root of 11 is going to be closer to negative 3 than it is to negative 4. If I were to plug that into my calculator, I would find out that's approximately negative 3.3. So there you have it. Last one. We're going to do the same thing, but this time without a calculator. First, we want to determine whether each number is rational or irrational. I'm going to bring our perfect squares list down to help us again. And then if it is irrational, we're going to find which perfect square, which number it lies between on the number line. Just like up here, we found the square root of 24 lies between 4 and 5. And up here we found the negative square root of 11 lies between negative 4 and negative 3. So let's do that again. We want to find out, is the negative square root of 30 rational or irrational? Well, is 30 a perfect square? No, it's not, because this list keeps getting bigger and it would have been here. So if 30 is not a perfect square, then this must be irrational, because it's not going to come out to be a nice number. The square root of 30 is not nice. It's irrational. But where is it going to lie between? Well, 30 is between two perfect squares. It's between 25 and 36, which means the square root of 30 is between the square root of 25 and the square root of 36. Well, what is the square root of 36? Let's just rewrite it. Square root of 25 is 5, and the square root of 36 is 6. So that means the square root of 30 must be between 5 and 6. There we have it. That's it. That's our whole answer. Yay! Let's do it again. Okay. Square root of 36, is that going to be rational or irrational? Well, is 36 on our list? Yes, it is. Here it is. It's right here. So the square root of 36 is 6. So that's going to be rational. Now, because it's not irrational, we don't have to do our number line thing. We know it's exactly 6. If we go back into our chart up here, we would notice that 6 belongs to the natural numbers. And because all the natural numbers belong to the rational numbers, it must be rational. Well, there you have it. Here's your nice summary, your key idea of the day, and we're putting it into practice down here. I hope you have a wonderful time on your homework.